Okay, we're continuing in chapter 3. We're building our tools that allow us to find derivatives quickly and easily. In this section, we're going to learn another tool, implicit differentiation. And we're also going to use implicit differentiation to find rules for inverse trigonometric functions. All right, so far we've been finding derivatives of functions that are defined by expressing one variable explicitly in terms of the other variable. So y of x, right? You have y on one side and x on the other side. Only x. Y on one side and then only a function of x on the other side. There are functions, however, that are defined implicitly. Here's the equation of a circle. X squared plus y squared is equal to 25. And so you can still view this like this is x squared plus y squared is equal to 25. You implicitly have y as a function of x, right? You can graph it like this. You see we've got y of x, right? And you can solve for y here, and you get plus or minus the square root of 25 minus x squared. So here's plus the square root of 25 minus x squared, and here's minus the square root of 25 minus x squared. You can find the derivative of this function, and then you've got the derivative of y as a function of x, right? But the first thing to notice about that is it's kind of messy. It's a lot, right? You're finding the derivative of two separate functions. It's not very clean. It's a lot of work. But then furthermore, this is a relatively simple case where you have y implicitly defined as a function of x, and you can solve for y. Here's another example. It's a lot more complicated to solve for y explicitly. If we come here, so here is that relation, right? But it's not easy to solve this by hand for y. And it talks about how a computer algebra system can do this fast, right? It's a computer, but it solves for different functions. So you've got like here's one function, here's another function, and you kind of add all those together. And so I guess you could get those functions, differentiate those with respect to x, but that's a big mess, right? There's got to be a simpler, cleaner way. Well, that's what we use implicit differentiation for. Okay, so it says, fortunately, we don't need to solve an equation for y in terms of x in order to find the derivative of y. Instead, we can use the method of implicit differentiation. This consists of differentiating both sides of the equation with respect to x and then solving the resulting equation for y prime. In the examples and exercises of this section, it is always assumed that the given equation determines y implicitly as a differentiable function of x, so that the method of implicit differentiation can be applied. Yeah, so like in an equation like this, we're assuming that y is the independent variable, is what it's saying. We're assuming y is the independent variable, and so it's implicitly defined, right? So if you come up here, right, you see it's kind of like this function of x is implicitly defined, right? So here y is implicitly defined, and then we're assuming that implicitly defined y of x, right? It's y of x. Y is the dependent variable. X is the independent variable. That y of x is differentiable. But I mean, if you do implicit differentiation here and you solve for y prime and you get a clean function, well, then it is differentiable. If it's not differentiable, then you'll discover that when you solve for y prime. So, and then they just do some examples. I'm not going to get into the examples here. We're going to, in the example problem playlist, I'll go through in detail how to do this. But in this problem, you see they're finding y prime for that equation of the circle. They find it, and if you come here, and the result they get is dy dx, y prime is x or minus x over y, right? So that's interesting. If you come back here, at any point on this circle, the slope is just minus the x coordinate divided by the y coordinate. So the derivative is a function of y. So the derivative is a function of the function itself, you could say. And so here it says, okay, the expression dy dx is equal to minus x over y gives the derivative in terms of both x and y. It is correct no matter which function y is determined by the given equation. So y is, when you solve for y explicitly, it's plus or minus the square root of 25 minus x squared. But here, those two possibilities for y are all built in. So it's a lot cleaner and a lot simpler to do implicit differentiation. Okay, here's another example. This example is with this curve here that we talked about. If you solve for y explicitly, you get this just big mess, right? It's three separate functions because here's plus or minus. So yeah, I guess you could take this derivative, dy dx here, but if you do it implicitly, here's y prime, right? Much simpler. And again, in this case, y prime is a function of y itself. Now, another example they give here, here's a relation where y is implicitly defined. You can't solve for y explicitly here. It's impossible. So you have to use implicit differentiation. Okay, so here's more examples. Here's three more implicitly defined relations. So they give so this here is this implicit function or relation. Here's another one. And we could do implicit differentiation and find y prime no problem on these three, y prime or y double prime. These are really complicated, so it'll probably be the derivative will be a function of y itself, but that's fine, right? Just for any of these points, plug in x and y, and you have the slope of the curve at that point. In the example problem videos, we'll do complicated implicit differentiations. I mean, these aren't that complicated. Okay, so here they find y double prime. We'll do examples of finding the second derivative implicitly as well. Once you learn implicit differentiation for just finding the first derivative, then it's an easy step to do the second derivative. Okay, so now it turns to derivatives of inverse trigonometric functions. And we do this in this section because y is the inverse sine of x is equal to y. Well, you can write that as sine of y is equal to x, right? So we do implicit differentiation to find y here. And that's what it does. So it finds the derivative of inverse sine, and then here inverse tangent using implicit differentiation. And that's how these derivative rules for inverse trig functions are derived. Okay, so now we've got even more tools that we can use to find derivatives quickly and easily. Here we've got derivative rules for inverse trig functions. And that's it for this section. See you guys in the next video.